All right. So read the last question there. Like the question we stopped at should be number 6, so is it number 7? Check for me. Check for me, number what? Guys, this PDF was posted on equilibrium of forces and moments. Huh? That's not the past one. I'm not talking about past question. I'm talking about the one on moments and equilibrium. One we posted from last class. If possible, someone help us and post it on that group again. That question, the PDF on moments, equilibrium of forces.
Physics past physics math.
Have you seen the question? Please find it. Yes, sharp. So that we can start solving. So this question, well, see, if you can't, but it's just that I want us to follow it one step at a time. So I said I find any question. Let me look at it. Do you have it? It's a PDF.
Yes.
This PDF, something sharp. The one that has moments of and equilibrium of forces. Please look at question 7. Look at question 7. It says calculate the weight of the log B necessary to keep the object A in equilibrium. So I want us to look at question 7 and question 8. Then we'll now start picking questions randomly from there. So question 7, calculate the weight of the log B necessary to keep the object A in equilibrium. So in that question, we have something like this. Let's be checking for me if I'm correct. Then I have Is it true?
Air. Oh, no.
So they called here A, they called here B, shall Then I put something like an arrow here. They said this one is what?
30 grams.
30?
Gram.
Okay. Is there any other thing?
Theta.
Okay, here.
Yes.
30 degrees. Is there any other thing? Check. So this is what we have there, children? So they're asking us that we should find the weight of this one, that will be able to keep this one in equilibrium. That's what they're asking us, that we should calculate the weight of the log B necessary to keep the object A in equilibrium. And you know, by equilibrium, they mean in a situation whereby this particular one is no longer moving. Hope you know. Because see, as this B is now, if its weight is more than this, it will move until it gets to a point where it will fall to the ground. So that this one will adjust, then stop, it will stop moving. Is it not true? Yes. And if maybe this one happens to be bigger than this one, it will drag this one till it gets to a point where it moves, maybe stop somewhere, then this one will hang, or maybe even probably come down to meet it. These are the two conditions we are looking at. So what is simply means is that for equilibrium to be achieved in this case, is either this object moves down or this particular object moves down. Are you seeing it? That's the condition there. So that means that we apply the principle of forward force minus backward force is equals to ma. And we told you that anytime we're talking about equilibrium, that acceleration will be equals to what? So that means that what I'm applying here is forward force minus backward force equals to ma. But at equilibrium, A is 0. So which means that everything here should be equals to what? So that means equals to 0. Alright, so please, what will be the force acting on this, the components now? Since we know there is forward force and backward force, what will be the components of those forces now? Yes. So please notice, Shebi, you see that this particular object, I know this is not blocking anybody, right? Notice that if I have this to be my inclined plane, and I have force on this A to be this way, okay. Yes. Now see, if I have these objects to be weight acting on this object downwards, notice that this is mass, right? But I don't make use of mass when I'm finding weight. Sorry, I don't make use of gram when I'm finding weight. I actually make use of kilogram. Is it not true? So before I will convert this to kilograms so that I can do mg, I need to notice that this component is not at 90 degrees for this inclined plane. So how do I take this weight, this arrow now, to form 90 degrees with this inclined plane? Because notice that what I have there is actually, notice it's still at an angle. Is it not true? Shebi? But notice that if, for example, I now come and say, I draw this component to go this way. Notice that what I now have is something of this nature. Is it not true? Which is 90 degrees. Are you seeing it? Yes. So this thing that I drew here is simply, I'm imagining that I'm taking this particular force, or whatever force I have here, or whatever weight I have here, to a component that will rotate it to 90 degrees. And when I do that, I'm taking it that this one is no longer part of the equation. It's now at 90 degrees. So we'll get to that. So please, first of all, gram to kilogram is what? Divided by 1,000, right? So which means that 30 gram is the same as what in kilogram? Kilogram, right? That means that the weight now will be equal to mg, which is 0.03 times 10, Shebi? So 0.03 times 10 is equal to what? 0.3 Newton. Somebody can choose to use times 9.8, but we like using 10. If you use 9.8, you're not wrong. So that means that the force acting on this object then is actually 0.3 Newton. So remember that I told you that anytime you have an object on an inclined plane, that instead of stressing yourself, you should simply take it that y is equals to cos theta and x is equals to what? Very simple. And remember that this particular thing I'm taking now, this is 0.03. If I'm taking it to y-axis to 490 degrees, it's now becomes 0.3 sine. Sorry, Shebi is y here. 0.3 cos theta. Do you still remember? Zachariah. Do you remember that if we are talking about equilibrium, first of all, we said that upward forces and downward forces must be equal. Is it not true? Vertical forces will also be what? Horizontal forces will also be equal. So I'm trying to say, okay, if I have this force this way, there's nothing like, they did not tell me at any point that force at an angle will be equal. No. So rather, I'm trying to put that force in such a way that it will be at the vertical component and also at the horizontal component. So since it's on an inclined plane, the vertical component of this force, will be when I have this to go in such a way that it's like this. Because notice that this thing means that I've rotated this force now to this point. Which I told you that if you don't want to use this, you can actually use that our old principle. And if I put this now in this form, that means that there's an angle here. Do you still remember? There will be an angle here now. Theta. Look well. There will be an angle here. And that theta that is here is going to be the same angle that is here. So that since I'm taking this now, this force is what I have here. Since I've taken it to 90 degrees now, it will now be taking it to 90 degrees to y. I told you on an inclined plane, I proved it the last time and I said I will not be doing this in this class. I said that when you are taking to y-axis on an inclined plane, you call that force cos theta. So since I'm taking this force to y, it's now going to be 0.3 Newton cos 30 degrees. Your silence is just making me feel like these people are not following. And what I'm trying to avoid is I don't want to repeat our last class where we started proving it from the beginning. Should we prove it? We should just solve, right? Yeah. So that means that actually the force that will be going this way, notice that if, for example, I have an object placed on this, this side is this x-axis, is it not true? So that means that every force going this way is called Wx, that is force on x-axis. Is it not true? Yes, force on x-axis. So if that be the case, remember that we said that when you have an inclined plane, anything that has to do with x-axis becomes sine theta, is it not true? Which means that our Wx will simply be Wx sine theta. While our vertical axis will just be mg cos theta. Do you still remember? Yes. So if that be the case, now I'm considering this. If this weight, notice this is on the x-axis this way. This one is simply the object itself this way. I'm rotating it to 90 degrees. Now this particular force that is here is going to simply be mg. Hope you know, because it's at y-axis already. So we are finding out all the components. The force that will be acting down this way is on x-axis. Wx sine theta, or you say mg sine theta. While the force that will be acting on this, since the weight is acting straight down, taking it to vertical components will be mg cos theta. This one will be mg cos theta. While the force that will be acting on this particular lock to bring it down will be just mg. So I can simply say, since I'm comparing these two, that is what weight do I need here in order to keep this one at a balance. And notice that the weight acting on this is going this way, is it not true? Let's say, notice that I consider the y-axis, Shebi. Let me now consider on the x-axis. Then when I say mg also will be equal to, if I'm considering the x-axis, it will be what? Mg sin theta. Hope you remember that when you did trigonometry, if you do cos the y-axis, you do the x-axis. And since we are doing x-axis here, since it's inclined plane, x-axis is sin theta. So this is now going to be that weight on the B for the x-axis is going to be 0.3 sin 30 degrees. Punch for me, what do you have?
0.15.
Okay. WB is going to be equal to 0.15 Newton. Now, since we've gotten, and please, when you are considering these weights, This object and this one, will it be moving into this inclined plane? Will it be moving down inside this inclined plane or rolling down this way? Let's say the weight, remember when we started, we said that there are two conditions necessary for this to be at equilibrium. If this weight is more than this one, it will drag it till it comes down. Is it not true? And it's going to be this way that is coming. Or if this one is bigger than this one, it will come down here and it will drag this one to a point where it will stop. Those are the two. Is it not true? Which means that the only forces, we are not going to be considering this one turning to this place because of the fact that this object cannot go inside here. So the forces acting on this is simply this way and this way. Are you seeing it? So when we are considering our forward force and backward force, we are going to be simply saying that it's simply going to be force on the y-axis this side and force on the x-axis, that is wx. So this should be our correct answer, not this one. Hope you understand it. Why? You said? Why you see now? See, we said we are considering the part that this ball will take and the part that this rock will take. And the only point that it will take is simply, yes, we know that we've learned that when it's y-axis, we are going to use cos theta. And when it's x-axis, we are going to use sin theta. Now we solve for the two. We are now checking that there's a question given to us, and that question says that at what point or how do we get this log to be in equilibrium with this? So for us to consider it, we will not be considering, can this object actually move in a way that it goes down here, in as much as the weight is happening here, and when we resolve it to the y component to be this, can it actually take part in any of these directions? It's not possible. But for equilibrium to achieve, this object can easily go down here, downwards, and it can also go down this way, depending on the weight. If this one is more than this, it will drag it down so that there will be no movement. At that point of no movement, we say that there is equilibrium. Or this object drags this one if its weight is bigger than this. At the point where it stops moving, there will be no movement, which means that equilibrium has been achieved. Or if possibly they are having the same weights, let's say their weights are slightly the same and they happen to just stay on this without movement. They happen to just stay on this. If you simply check it, you will see that the only possible ways of movement is simply this object going this way, or any little touch, it's going this way. So that is why I'm not considering these parts of this force. So that is why after solving for the two, we now said that we are not going to make our answer to be in such a way that it obeys this rule, which is forward force must be equal to the backward force. And what is the forward force here? It can be this one when the weight is bigger than this, or it can be this one when this weight is bigger than this. So whichever way, see the axis we are considering for this. So that means that this is the correct answer. That is the weight on x-axis and the weight on that vertical axis, and not the vertical axis component to the other. It's not confusing.
Is it that we're looking for the one that is?
Read the question. The question says that at what point, read that question and so that you understand. We are not just displaying here. Read out the question. Read the question out.
Calculate the weight of the log B.
Calculate the weight of this log B, Sherry?
Yes. Necessary to keep the object A in equilibrium.
Now, see, calculate the weight of this log B, necessary to keep this one in equilibrium, which means that they are asking us that in this case, this log is bigger than this. For it to keep this particular one in equilibrium, it simply means at what point will this one move to, so that there will be no movement again. So that this one now will be in equilibrium, because we know that at equilibrium there is no acceleration. So if this log wants to move now, you now that is asking me, between these three forces that I have, when you are resolving this way, when you are going this way, and when you are going this way, if this log now happens to move, or anything that concerns it with regards to this ball, in what directions will it move? It's either it move this way or it move this way. And provided they are asking us at what weight will this one keep this one in equilibrium, it simply means that this one is bigger than this, because it's the one keeping this ball in equilibrium. So it will have to move down, so that it will stop moving. So at that point where it stops moving, let's say this one adjusts and comes somewhere here. So they're not asking us, what do we need? What are the weights responsible for this to give this in equilibrium? It's simply going to be, this one now becomes forward force. This one now becomes backward force. It's very simple. But assuming maybe they told me that a hole is dug inside this and this thing falls inside here, that's why I will not be checking any other component. So it's simply the forward force here will be equal to the backward force. And remember we said that weight on x-axis is going to be equal to what? Mg sin theta on an inclined plane. Ask. Okay. Go on. Okay, which one?
Since you said the first article on that inclined plane, that was an equation. But we're not considering friction because it's an equation.
Yes.
So we're going to do, all I think we're going to say tension minus mg sin theta is equal to 0. You find that tension will not be the mass of that. Finally, you still get 0.15.
What you just said is the same thing with what we did. What you just said, do you know why? See, do you know why? See, do you know why I said that what you just said is the same thing? Because if you check it, if you still carry mg sin theta, mg sin theta minus mg is equals to 0. It's the same thing with what you said. Okay, resolving. Because we resolved it. No, I have to teach you everything. Hello? Please, I'm on my class. Okay, see. Okay. There is any force on an inclined plane on the x-axis. Yes, it's given as mg sin theta. Yes. It's mg and the mass, yes? What you are saying is what we've done here.
So what I'm saying is that the resolving is when the issue will come. Yes.
It's not supposed to be an issue. No, it's not supposed. That's why you're a student. See, do you know one thing? It's easy when you have options to look at for you to come up with something. It is different from when you really know it. If you have option, why you're saying that thing is because you're looking at what we've done and the things around you. But it is different from when you are having to generate. You are seeing a question. You have to look at that question, go through certain principles to consider an answer. That place now, you see that all these things you are saying will not be easy for you again. So please, relax. So please, what I'm trying to consider is simple. For the fact that they said that these weights, for the fact that they said that this thing, that we should check what we need from this to keep this in equilibrium, is simply the same thing as saying that when we check all the forces on this inclined plane, we now see that we have no use for this. So we are now considering if it's going this way, which is Wx, and when it's going this way, it should be equal to what we have here, and the weight that will be happening here is just mg. So which means that forward force here, if this is the forward force, it should be equal to what is happening here. Or if this is the forward force, it should be equal to what is happening here. It's not hard. All right.
So we're actually learning.
Okay.
But I want to say something. Let me just spot it. That of school, but so I want to drive home a lesson. They say just like that thing on the cross. They say you not. They say you must fast, you must meet Christ before you meet God. But he just meant. He said you must meet Christ before you meet God. He just met Christ. He went to heaven. So if I can do T minus mg sin theta, I don't need to be doing T
minus mg sin theta.
Yes.
Hope you know that. Wait now. Hope you know that T is the same thing as tension. Should be on a string, and that your T at this point is going to be m what? Is it not mg?
Yes.
Is it not? So what are you saying?
It's the same thing. It's what I'm saying.
But he's trying to.
See, please. Hello, please. Okay, go ahead.
I think I'm just trying to tell you that you don't need to resolve all the things. Check whether it is empty.
No, see. Why he's saying that is because he's looking up whatever he has. Me, I'm teaching you based on the fact that I want, if you see this inclined plane question, you are able to check all the forces there and make your choice. Once you learn it, you plant it now. This one is because we are still learning it. Alright, go ahead.
I just wanted to say that check whether it is without having to resolve.
Okay, I'm gonna see the reason why we started with this is I'm just actually saying, since we know that on an inclined plane, the y should be mg cos theta, should be? And the x should be mg sin theta. Is it not true? Now check everything we've done here. There is no reason for this object to actually go this way. Is it not true? So it's either it's going this way or it's going this way. It's very simple. Which, in fact, see what is there. When I teach you, you feel like there are reasons or options you have. Go through your options. Then when you run around and should I say, come to a point where you really understand it, you see that what you are doing is still running around what we have. So what I'm saying is we check all those force components and we are now checking those the balls. Which directions will it go? There's no way that ball will go down inside the inclined plane. It's not even possible. So if you're using your normal eye, let's say I put an inclined plane here or something that is bent, I keep a ball on top of it, carry something and attach to it. It cannot enter inside now. It's either it's going this way or it's coming this way. So that's what we've done. So the extra detail is just for those of you. I believe that there are students here that don't have time to check AI. Hope you know. Because once I'm teaching you, there are some students that their job is to simply be googling AI, be checking things. There are students that are not like that. Their own drill is just come to class, let the teacher teach me, let me understand. So we have to start it from that scratch to that point. So please, this is what you should do. If you do it and over, you see that you will master it. It's not hard. So simply, the first thing that will be acting here is simply the one going this way and the one going this way. So that is it. So that means that my answer is going to be this because WX is going to be mg sin theta. And why here, the first acting here is only vertically simply means you are just considering mass and gravity. So this is my final answer. This is the correct answer. All right, please read question 8. Should I claim? Be fast. Be fast. Read question 8. Are you not aware that when I taught you dynamics, that I told you rope, should I say force on a rope is not tension. That's the principle of T minus mg sin theta. That's what I taught you that time, man. Yes. This is inclined plane. You must understand the concepts. This one is inclined plane. I want you to understand all those concepts. All right, please read question 8 out. Read question 8 out. Let's. Question 8. A uniform ladder of mass,
100 kg at 60.
100 kg,
At 60 degrees.
meets.
Lean.
Okay. At 60 degrees, yes? To the horizontal, Against a frictionless calculate reaction on the wall. Any other thing? No. Okay. Just like a question like this, you just need to build that habit of analyzing the forces. A question like this, you come and do T, this one. You tell me you get the answer. It's not possible. You must build that habit. Build that habit. So let me just draw the ladder. Let's start with the ladder. So I have a ladder that is leaning. Now let's say this is your wall. If this happens to be my wall, I said that this ladder raise at 60 degrees to the horizontal against the frictionless wall. So let's say this is my 60 degrees. Okay. If this is my 60 degrees, then they are asking me for the reaction on the wall. That is somewhere here. Somebody wants to ask me, how do I know it's this place? Notice that there is also a reaction here, but this one is from the ground. Is it not true? So that is how I know that that is the reaction from the wall. So this place, because as it's resting on it, there will be an equal and opposite force from Newton's third law that will be reacting it back. So that's the one they're asking me. Why? Assuming they ask me, what will be the reaction from the ground? That means the one I'm considering is this one that is here. RG, reaction on the ground. That's the one I'll be considering. Assuming they ask me, what will be the friction? What will be the friction on this ladder? Then I will not be considering this point, because notice that if this particular ladder is this way, if it's not experiencing friction, it will easily slide. That means that there will be friction acting this way, because friction acts in the opposite direction to where the force should go. So that this one will be my friction. If you don't build this habit of getting these things out, you will see that questions will come. One way or the other, it will trick you. So build that habit. Then the next force now, once I've done this, the only forces I'm considering now is now the force acting on the ladder itself. So if I go to this ladder, what are the forces acting on the ladder itself? This ladder now. I've considered the environment. Remember what physics is. Physics is simply the study of matter and its environment. It is different from chemistry, because chemistry deals with study of matter. Change is that matter. It's more like chemistry is going inside to look at what matter is, what is happening to matter. It's proper. Why physics? You always consider the environment. So I've considered the environment, those are the forces. Now this ladder that I'm giving will have its weight. Is it not true? And we say that the weight of a ladder acts, the weight of an object acts downwards towards the center. So let's say this is the center of this ladder. Now, remember we said that weight normally acts vertically downwards. Okay, so let's say I have my weight this way. So let's say this is weight of the ladder, WL. So remember that we have frictional force this way. Okay, they did not tell us that a man is on the ladder. Is a man on the ladder? No. Unlike the one we did in our last class, there was a man on that ladder. So since there is no man on the ladder, we are just going to consider what we have. We are considering what we have. But see, let's check again. Did they give us the measurement of this ladder from here to here? Did they give us? They did not give us. Okay, that means that the length of this ladder is actually going to be from here to here is the length.
Mass of 100 kg.
Okay, this one is mass of 100 kg. That is, the ladder itself has mass of 100 kg.
Yes.
Which means that the weight of the ladder will be 100 kg times 10. But do it for me. What do you have?
1,000.
1,000 in Newton. Is it true? Ahead. Okay. Now, so the length of this ladder should actually be considered to be L. Is it not true? Why from this end to this end and this end to this end should actually be considered to be L over 2. Do you agree? Should we agree? Very important. What we call this thing, in as much as I'm putting the values beside it, but what we call this is something of free body diagram. I must use it to analyze this. So I've been able to get that from the center, which is where the weight is acting, up and down. It's going to give me that length divided by 2. Why I'm putting it is because I'm dealing with equilibrium. And in equilibrium, I told you that there are 3 things to consider. Upward and downward force equal. Horizontal forces, which is also called clockwise and anti-clockwise moments. Then torque. Do you still remember? And remember that for you to do torque, you normally consider perpendicular force and distance. Hope you still remember. So because of that torque, that is why I'm putting down my L and my L over 2, because I cannot talk about the force without talking about the length. Very important. Alright, so if I know that, let's try to remember the principle I taught you. In our last class, I told you that since we are talking about this one, to find the equilibrium of this reaction on the wall, or to find the reaction on the wall, I will simply use torque. Remember I told you using torque is a shortcut method, where we point everything to one side. So it's even easy for us here. So let's point all the forces here to this point. So which means that we are making here our fulcrum, our pivots. Because at the point of pivot, or the point of that fulcrum, we are not considering its turning effect. See? So if we know that, let's use it. So we'll do sum of torque will be equals to 0. Sum of torque will be equals to 0. And if we check it, it simply means that clockwise torque will be equals to anti-clockwise torque. Will be equals to anti-clockwise torque. So please, let's check. Before we put this now, let's check which one will be the clockwise torque here. If we are considering this arrow, hope you know that this arrow now is not at 90 degrees to this ladder. Are you aware? See now, shall we remember that torque is simply, if I have a force like this, I will need to resolve this force so that it will become this way. Is it not true? And when I'm taking it to this part, what I have here, I told you always consider the force to be y, consider the horizontal distance to be your x, the distance. So if I'm taking this now to y, what will I have? Let's say there is an angle here, theta. If I'm carrying this away from the angle, sine, Shebi? Yes, this is our normal thing that we know. But remember what inclined plane talks about.
Yes, that's
So let's carry the angle. Let's use that our approach that we used that day. Notice that I have this. Let me bring it, the ladder. Notice that I have this. Now this force that is here is also here. So parallel forces are equal. Is it not true? Now notice that I have an angle here. Let me bring that angle. So let's say this is my 60 degrees. Now, this is that my RW. So I want us to know the angle we are using now. So let's say we want to now make, because torque requires everything being at 90 degrees. If I'm carrying this thing now towards the y-axis, what am I using? Cos, Shebi? So that means that if this thing is coming this way now, I will now have that the angle I'm using for us to resolve this is going to be what? Cos theta. And remember I told you that once anything is at x-axis, on an inclined plane, that instead of you stressing yourself, just use cos. Should you see the reason for that now? And if it's on y-axis on an inclined plane, instead of you stressing yourself, use.
Wait,
is it true?
they use cos.
For why you use cos, Shebi? Y-x you use what? Sine. Okay, sorry. So with that said, if I'm carrying this thing now towards y-axis, notice I'm going away from the angle. This angle will be opening now. Away from the angle, is this sine or cos I'm using?
Fine.
If you put us in trouble now, you know.
Wait.
See, we've been able to put the ladder out. Then we draw down our force. This is the angle given to us, Shebi. If we are carrying this now to y-axis, will this angle be opening or closing? When it's opening, it's going away, Shebi. And away from the angle, we use what? Then towards the angle, we use what? But because of the fact, why I'm doing this is because some people are just joining us and they might not understand what we are doing. But please, for us to make things easy for us, ourselves, and because of the fact that it's objective we are going to the right thing, let us stop finding this angle. Let us just have it in mind that once it's an inclined plane, the y-axis will be equal to what? Cos theta. And the x-axis will be equal to what? Yes. So if you want to see how we proved it, you go and check our videos and remember it. But for now, to make this easy for ourselves, just notice somewhere. If it's an inclined plane, y-axis I use cos theta. X-axis I use sin theta. And we know that normally, y-axis should be sin theta. X-axis should be cos theta, Shebi. So when it's inclined plane, do the opposite. So I will not be doing that thing again. Let me just be using it. So I would simply say that this will be the same thing as saying RW, the first I will use for arrow will be RW, since it's on x-axis, sin theta. Yes, this was on x-axis, this is x-axis. Now, there's also a force here, is it not true? That is weight of the ladder. And notice that anything going this way is vertical, y-axis, Shebi. Since it's on y-axis, WL will now be cos, the force I will use will now be cos theta. Very simple. And notice that's the only force there. Because these two now, these two, the friction and the force on the ground, reaction on the ground, we made it our fulcrum. Because they are the same points. So we made it our fulcrum. That is, we are directing all the forces to these points. Remember that our shortcut. So if we know that, we will now consider which one is the clockwise moment out of these two forces and which one is the anti-clockwise moment. If this one is going to meet this fulcrum, if we are directing all the forces to this fulcrum, it will be moving this way. And this way is what? Is it clockwise? And we say that in circular motion, clockwise is always what? Do you remember? And then, this particular one, if it's going this way, it's going anti-clockwise to meet this fulcrum. So, and anti-clockwise is what? Positive. Alright, the next thing we need to check, since we are considering torque, is that if we have these forces at 90 degrees, if we resolve to 90 degrees, we're now going to be checking the distance. And here, distance is given by length, because they did not give us length. So we check, from this RW to this fulcrum, what length is there? Is the full length, is it not true? From here to this point. That means I'm going to be considering times L. I've not started putting it in clockwise equals to anti-clockwise. I'm still bringing out all my forces. Then, from the force, that is this particular weight of the ladder, to the fulcrum, what is the length? L over 2, that's half of the length, Shebi? So, times L over 2. So we said that this one is clockwise, this one is anti-clockwise. So obeying the principle of clockwise and anti-clockwise torque must be equal. That is where I now put all those things in correspondence. So that I will now have clockwise torque will be equal to anti-clockwise torque. And we know that when we are putting this thing in its equivalence, we don't have reason to put that minus, those signs. Shebi, you know. But if we want to do it, we can simply say that it's the same as saying minus reaction on the wall sine theta times L plus weight of the ladder cos theta is all equals to 0. I see that when this can cross the equality sign, it becomes, that's why I normally tell my students, don't consider the signs. It's okay to pull it out, but the best way is just make it this is equal to this. So that if I'm using that principle, I will now have that my clockwise is going to be simply RW. And RW, we got that weight, this RW, what did we get it as? That's what we are looking for, Shebi? Yes. Okay, so we just say RW sine theta times L is equals to weight of ladder cos theta times L over 2. This process might seem like it's long, but when you study it over and over, it will make sense to you. And one thing is that once you learn it, you've learned it. There is no place you will be going at some point. You will see that there is a question that involves weight on a ladder, and you are using a different approach. No. So once you are using these our procedures, analyze it, get to see how it's coming. You will always be right. Because we are preparing you to pass exam. Alright. So now let's put things in order. The sine theta here is going to be sine 60. Yes. Sine 60. Then I have my RW. Then this is my L. Is equals to weight of the ladder. What's the weight of the ladder? We got it to be 1000 Newton. So we got 1000 Newton cos 60. Now we have L over 2. You know why we are not replacing that L with anything is because they did not give us length. So any question on linear ladder static equilibrium, if length is not given to you, don't say, what if I'm not giving length? No. You will always make use of that length that is given. Check when it's half. Check when it's 2/3. When it's 1/3. So in this case, what we just have is a situation where we have the length and half of it. So now let's check. Notice that immediately I see 2 here, I see 1000. 2 can go here, 2 can go here. Let me see. So that I now have 500 Newton cos 60 is equals to. What do for me? Sine 60 is what? 1. 0.8660, shall we? Times L. Well, notice, I have L here now, and I also have L here. Is it not true? They can cancel out. So I can cancel this, cancel this. What do for me equals 60.
0.5.
So 500 Newton times 0.5. Okay. So you got what? Thank you. Okay, then I now have, this is essentially saying I have 0.8660 RW. Hope you know. And this one is 250 and it's in Newton. Okay, yes. Then I can say, to make this sort of formula, yes, I will divide both sides by 0.8660. So that this will cancel this. So for punch for me, what do you have? 288.6 in Newton. That will be your final answer. That will be your final answer. So please, I want you to always get to the habit of drawing free body diagram first. Very important. Because good number of you are used to all those your Google and AI. If you competence, you know what I mean, imagination. Stick to free body diagram. Very important. You do it over and over, it becomes part of you. You need to able to speak. So that's the answer. Can I clean? I ask. I should come. Yes, Maybe this is the weight of the ladder. Gravity acting downwards. This is what we got. Now, everything we are resolving is more like, say, if I want to resolve this, notice that this ladder's 90 degrees is this one. Because if you keep it straight, that is it, the X. And so that means, let me say I'm putting this thing around it. Should you see? Now, let's say I have this now to be an angle. Now, notice that if I have this, if I have this, my force that is here, and I have this thing that is here, this thing is 90 degrees, should be? If I have it to the 90 degrees, what weight? They gave me an angle here. It's 60 degrees, right? If that angle is 60 degrees, what angle will be here? Every angle must equal to 90, should be? So 90 minus 60 is what? That means there is 30 degrees here. Is it not true? But now check. Notice that automatically this particular line and this line forms another 60 degrees, another 90 degrees. Is it not true? So if what we have here is already 30 degrees, that means there's an angle here, which is 60 degrees, right? Do you know that this line I'm seeing here is simply this same line that I've taken to this point? I've taken this line now to this point. That's what I've done. Now, when I've done this, now let's say I now have this now to this. If we are looking at this now, this particular thing now. Now, let's say if this is looking at this, what angle is showing them? Opposite, Shebi? But I have no business with this opposite. Because the one I have business is with the mg that I resolve to this side. Is it not true? And when I resolve this mg to this side, it becomes adjacent. This part becomes my adjacent. Watch. If this part becomes my adjacent, and I already have this WL, this side, before I resolve it. So I'm now left with adjacent and hypotenuse. And whenever you have adjacent and hypotenuse, what does it mean? Cos, Shebi. So if you use CAM, which is adjacent over hypotenuse, if you cross it over, you see that you are not making use of this side and this side. You have no business with this side. That is one way to do it. But if you don't want to start stressing yourself doing all this analysis, that's where we now said, stick to that and we're bringing it out. That is, if I come and see this thing now, wait, let me clean this. Please, you need to go and check my first video. The first class. That is why that first class. The first class, I just took time in the first class there. All I did in the first class was just teaching how to find angles on an inclined plane. So if another way to do this now is, let's say I just come and say this ladder that is here, just this ladder, I bring it out. Then this particular weight that is here, at this point, we have something parallel to it this way. Let's say I put it here. Now notice that there's an angle here. So this is the ladder. This is the force. This force that is somewhere here. It should have a parallel force as well this way. So if I'm going to make, my goal is always, whenever I'm finding tall, how do I make everything to be equal to 90 degrees? So if I'm carrying this thing now to this place, will I be going towards the angle? Will I be closing this angle or going away from the angle? I'll be closing it. And towards the angle is what? Cos, Shebi. That means that what I'm using for this y is simply going to be cos theta. That's the second way. But if you don't want to be stressing yourself doing this thing that you see inside the exam hall, all these things you are trying to do is very hard. You need to pay attention, study our first video where you understand it. But if you don't want to be doing this thing, remember that in our normal vector class, we said that y-axis is always sin theta, x-axis is always cos theta. Instead of doing this thing, just know that inclined plane is the opposite of it. X now becomes sin theta. Okay, you now understand it. So still go through that video over and over. So let me give you one like this to solve for me. Before you ask questions, let me give you one. Ask so that when I give you one to solve. Okay, why is it minus? Why is minus is now we are now checking if it is going in clockwise or anti-clockwise direction. Now see, this arrow W, if it's going this way, notice that we are pointing everything to the fulcrum, Shebi. If it's going this way to this fulcrum, is it going clockwise or anti-clockwise? Eh? That is, this way is clockwise, Shebi. Yes. If it's going clockwise, remember in circular motion, we said that clockwise means minus. That means this one now that is here, if this one is going to this fulcrum this way, is it going anti-clockwise or clockwise? Anti-clockwise, anti-clockwise is positive. So, but if you don't want to get all those signs to come and do everything equals to 0, remember I said if you don't want to do this thing, you can just say, since there are two forces, just say point this, that is forward or upward or backward force is equals to forward force, or you say upward force equals to downward. You can just do it this way, clockwise equals to anti-clockwise. So which, okay.
So that vertical line that is pointing to RG is parallel.
This one now?
Yes, it's parallel to the one pointing to WR.
This one now?
Yes.
We didn't consider RG because we said when we are considering anything using torque, we always consider all the forces to one side or all the forces to the other side. You need to guys. Do you know our problem now? No. You people don't study. That's the truth. In every class we are repeating what we've done. Yes, because assuming maybe when we finish our last class, even starting from the one we did at mass communication block, assuming after that class you people took time to observe that shortcut, you won't have this issue. Because I told you, if you want to use the normal procedure, follow all the two rules of equilibrium. Upward, downward force, equal. Clockwise, anti-clockwise, equal. That is sum of parallel forces, or torque. Clockwise, anti-clockwise, torque, equal. Now, I said instead of doing those three procedures, the simple and shortcut is simply use torque. Point all the forces to one side, making one side the fulcrum or the pivots. Then you find all the forces this side. Then you check what you are looking for in this side. Or if you want to find force this way, you make this side your pivots. And when you have a pivot, you no longer have that turning effect. You point all the forces towards the side. You say?
That one is moment.
That one is moment. You are using the same principles of moment here now. Do you think moment, what do we define moment as? Moment is the turning effect of force, is it not true? Now, when that turning effect is at a point, it becomes torque. A moment at a point is also known as torque, which we said is the force at perpendicular distance. Product of force at perpendicular distance. Is the same thing. It's the same thing. I'm the one to teach you. Yes, not AI. Their problem is that as you are teaching them, they are punching all those AI Google search to do one or two things. One thing is sure is that thing will teach you to its own limits. But we will teach you not just to the limits, but to the standard used in university. So that one will just go to its limit, its own scope. So that is why if you see me do it this way, I stretch to this other end, stretch to this other end. So when you are considering moment is not only when you have horizontal force, on a ladder as well. When you are considering that moment at a point which is tall, it's still the same principle. I ask. Okay.
Please, can you just explain?
Okay? Eat before coming. Stop drinking garri. Yes. Where and where do you want me to start from?
Beginning.
That's why I said let me give you question 2. So that you solve that one and be checking and be getting yourself. Yes. Shall you see? Notice that even in your textbook, that they did not do this. They just gave you the question there. Sherry, but they gave you questions like this there, but they did not teach it. That's why when you then come into exam and you see certain things like this, look as if the world is turning around, but it's not. So please see what you do for me. What you do for me now is I will give you a question that you will try. The minute I finish going down to check, we will now come down with your utmost attention and solve it together. Are you there? So when I'm now solving that question, you pay attention from the beginning. And remember that everything we derive here, what we are only making use of is talk. We say that talk is a shortcut. That with talk, all we just need to do is to point all the forces to one side. Or if we are finding force here, we just point everything to the other side. So, right. So when we are done with this question, we'll now solve together. A uniform ladder of mass.
Daddy. Somebody wants to say something.
Right, first. A uniform ladder of mass. A uniform ladder of mass, 70 kg. Don't worry, whatever question she has, when I'm solving this second question, she will understand. A uniform ladder of mass, 70 kg. Leans at 30 degrees to the horizontal.
Of mass, 70 kg.
Yes, a uniform ladder of mass, 70 kg. Leans at 30 degrees to the horizontal. A uniform ladder of mass, 100 kg. Leans of 70, sorry. Yes, leans at 30 degrees to the horizontal against a frictional wall. No, this one is a frictional wall. Against a frictional wall. Against a frictional wall. Are you there?
Yes.
Against a frictional wall. Calculate the reaction on the wall. Calculate the reaction on the wall. Calculate the reaction on the wall. If coefficient of static friction, calculate the friction on the wall. If coefficient of static friction is 0.84. If coefficient of static friction is 0.84. So I said a uniform ladder of mass 70 kg leans at 30 degrees to the horizontal against a frictional wall. Full stop. Calculate the reaction on the wall if the coefficient of static friction is 0.84 not Newton. It has no units. I've taught it before. So we call it mu is 0.84. I have solved. So once you are done solving, just signal me, let me check. Then you now pay attention. So we solve it together and you understand.